Okay, up to this point, we have already talked about the parameters of a normal distribution, and we've talked about how we can come up with the maximum likelihood estimate for those parameters. And so again, if we're assuming that our data are random variables drawn from a normal distribution, that normal distribution has some mu and some sigma. And what we did is we figured out how can we come up with our best estimate of mu and how can we come up with our best unbiased estimate of sigma. Again, the mean and the standard deviation. And so hopefully now we have some idea of like what makes up a normal distribution and why, well, basically why we might want to figure out how to estimate mu and sigma, because otherwise we're not going to understand the underlying distribution that we think we're sampling things from. So what we'll see is that it's often easier to interpret data if they are modeled in a way that meets what's called a standard normal distribution. And a standard normal distribution is simply a distribution that has a mean of 0 and it has a standard deviation of 1. And so essentially what we're going to do when we come up with a standard normal is we're going to remove the units in which that original data were measured in, and we're going to put them into units of standard deviation. And over the course of the semester, behind the scenes, and we'll talk about the standard normal ad nauseum, I promise, behind the scenes, that's what most of the math is actually doing when we do things like regression or whatever we might be doing to model that. And so how would we go about transforming our data so that it meets the expectations of a standard normal distribution? So there's going to be two parts to it. Remember, a standard normal has a mean of 0 and a standard deviation of 1. And so we can start by centering our data. Okay, so I'm going to take each of our data, and subtract it from our estimate of mu. And that's going to center the data. So now, if we were to do this, the mean of the outcome of all of this, would be 0, right? Because everything is going to be centered around the mean. So the new mean for this is 0. So that's centering our data. The next thing that we'll do is we will divide it by the standard deviation of y. And by dividing it by the standard deviation of y, now we have what's called scaled our data. We've now moved our data from units that were in whatever units we measured them in, stones, furlongs, centimeters, doesn't matter. We divide it by the standard deviation. Now it will be in units of standard deviations. And that's because if we think about it, standard deviation is in the same units that we measured it in, and then obviously our data are in the units that we measured it in, and we'll just cross those out. So if this were kilograms, we would do this, and then we would end up with something that is simply in units of standard deviations. This type of a transformation is usually referred to as a Z transformation. They're also called normal deviates. They are called standard scores, or just simply standardized data. And so we can think about an example of why it's useful to think about things as being on units of standard deviation instead of in the raw units, because when they're in the raw units, we can easily get lost in those units. And so as an example, I have the story problem that's on the handout where say that we have data on African elephants, and based on previous work, we estimate that a male or a bull elephant will weigh 5,200 kilograms, and it will have a standard deviation of 1,450 kilograms. And let's say that for cow elephants, the mean is 2,600 kilograms, and the standard deviation is 320 kilograms. And we, assuming that we have a large sample of elephants, we know how both of those estimates were calculated. And so now let's say that you were to go out and you find 2 new elephants. And one of those is a male and the other one is a female. And let's say that the male weighs 6,700 kilograms. So the new male, new dot male will get, what did I say? 6,700 kilograms. And we get a new female. And let's say that it weighs 4,100 kilograms. And so what we want to know, and we can even keep track. So male mean is 5,200 with a standard deviation equal to 1450. And female mean is, what did I say it was? Somewhere up here, 2,600 kilograms and a standard deviation of 320. Okay, so this is what we know based upon previous work. And now someone comes in and says, hey, I found these two new elephants. This male elephant is 6,700. The new female weighs 4,100. And so, first of all, we'd look at that and we'd notice that the male is certainly bigger than the average male. And the new female is certainly average than, or is certainly greater than the average female. And so we might want to ask, which one is the more extraordinary elephant? And yes, I agree, all elephants are extraordinary. But if the whole universe of elephants, given this population, which of these two elephants might be most extraordinary? And so first I'll point out that the new male, I put that in there. And so the new male is 1,500 kilograms greater than the average male. And the new female, I guess I could actually use that since I went ahead and I did it. The new female totally, yes I did. I'm gonna just use the numbers, getting thrown off by my own brilliance. Copy minus average female. And so both of these elephants are 1,500 kilograms larger than the average. So the male is 1,500 kilograms larger than the average male, and the female is 1,500 kilograms greater than the average female. And so we might be tempted to say, well, they're both equally as extraordinary, because who doesn't think elephants are extraordinary? They both weigh 1,500 kilograms greater than what their average is. But when we convert them into units of standard deviations, which we can do, let's do that first for the male. And so I will divide it by the standard deviation for a male. We see that that male is roughly 1 standard deviation greater than the average male. And we can likewise do the same thing for females. And that female is roughly 4.7 standard deviations than the average female. So even though their actual difference from the mean was the same, given the underlying variance and standard deviation, I guess, of both males and females in that population, the female is clearly the more extraordinary specimen, right? That female is 4.6 standard deviations greater than the mean, whereas that male is only 1 standard deviation greater than the mean. And so this is an example of where standardization can come in handy, because you can actually start to think about, you know, where do individual datums fall on that distribution. And again, if you just looked at the raw difference from the mean, they both seem to be equally as extraordinary. They're both 1,500 greater than the mean, but taking the variation into account, that female is much more extraordinary than that male. That is a really big female. Okay. The other nice thing about standardization is that you don't have to worry about the units at which things were measured. And so we can take an example. And here I have inches. So let's say I measured things in inches, whatever what I have here. Looks like I have 9 inches measurement. And so now the mean inches is 4.4 and the standard deviation is 1.5 inches. I could then convert that into centimeters. So simply taking inches times 2.54 and then take the mean and the standard deviation in centimeters. And now the mean is 11 centimeters with a standard deviation of 3.83. And that's fine. We can always convert this. But if we were to z-transform them, they would be the same. And they are just the same data, right? I mean, we measured something in inches and then we converted that to centimeters. They're the same things. They're just measured on a different scale. One is measured in units of inches. The other is mentioned in units of centimeters. But just eyeballing the results, you know, it looks like, well, in centimeters, it certainly looks like the standard deviation is bigger than it is when we talk about inches. And since they're the same data, that can become kind of confusing because it's the same information, just on a different scale, but because standard deviations are in the units at which we measured them, just like the mean is, it's difficult maybe to compare those two things. And so we could go ahead and we could transform that, zinches. So I'm going to z-transform it, so I'm going to call it zinches, not zinchines, zinches. So this is z inches. And there's the longhand way that we could do that. We could take all of our measures of inches and subtract them from the mean of inches and divide that by the standard deviation of inches. And so now all of our data are in units of standard deviation, and because we've z-transformed it, the mean should be 0 and the standard deviation should be 1. So we say mean of zinches. I'm going to argue that that's pretty darn close to 0. That's just the computer being confused by rounding problems. And then I'll go ahead and I'll say, well, what's the standard deviation of my zinches? And it's 1. The shortcut / easier way to do this is there is a built-in function in R called scale. And what scale will do, you can see in the yellow there, the default is x, first of all. X is the data you're going to give it. Center equals true. That means that it's going to do this top part here, each observation subtracted from the mean of that observation. So that'll put everything relative to the mean. So you'll have just as many negative points as you have positive points. And then scale equals true is also equal true. What scale means is that you're going to divide it by the standard deviation. And so if I were to go ahead and put zinches in there, and now ask for the mean of my new zinches, it's again going to be pretty darn close to 0 because it is 0. And the standard deviation of that is 1. And then I can do the same thing with z centimeters. Let's call it zcm. I will z-transform that. I will z-transform my centimeters. And then again, I could ask for the mean of z in centimeters and the standard deviation of z centimeters. So the mean, whoppingly close to 0 because it is 0, and the standard deviation is 1. And in fact, if we look at the actual raw z-transform data, this is the new value for the first observation in inches. It's negative 0.29. And in centimeters, it's the exact same thing. So even though the actual values of the data are different because they're measured on different scales, once we z-transform them, we know that that very first observation that we saw is 0.29 standard deviations below the mean. And we know that the second individual is 1.69 standard deviations above the mean, and so on. And we get the same whether it's in inches or in centimeters. And that's pretty nice because that means that if we're always able to z-transform things, the units at which we measure things doesn't really matter. And so, you know, if you had, for some reason, if you only had access to a really old scale that did things in ounces, and you're like, I don't know what to do with this, and all the person gave you was the mean and the standard deviation of what they observed in ounces, you could always z-transform that, and then any other data that was measured in ounces you could compare against, you know, milligrams or whatever else you would want to. And so z-transformation ends up being a really handy thing, and as we'll see when we start building models, it'll make a lot more sense. Our parameter estimates will make a lot more sense and be easily interpretable if they are standardized, if they are in units of standard deviations. And so we don't really care what the units are measured in. As long as they're reliable with some level of precision, I don't care if you're giving me pounds or if you're giving me stones or, you know, or you're giving me kilograms. It's all going to be the same. And so once we have our standard normal distribution, we can start to make some predictions. And again, all of this only works if our underlying sampling distribution is actually a normal distribution. If it's not a normal distribution, then the mean isn't going to mean what we want the mean to mean. And if the mean doesn't mean what we want the mean to mean, that means the standard deviation won't mean what we want the standard deviation to mean. So again, that's why there's this important assumption of normality, because unless our data are normal, we can't really use the probability density function for a normal distribution. And so once we have a good estimate of the mean and the standard deviation, we can start to make predictions about where we expect things to fall in our population. And so in general, we would expect 50% of the data that we have to fall between the mean plus or minus 0.674 times our estimate of the standard deviation. Make sure that that is big enough so everyone can see what the heck I'm doing. What are you doing, Jen? Yeah. So we expect 50% of our data to fall plus or minus 0.674 standard deviations from the mean. So a nice place to start is, let's go ahead and assume that we're dealing with a standard normal distribution, which means that mu is 0 and sigma is 1. And so for now, let's just ignore that because it's 1. So we don't have to multiply anything by it. And so we expect 50% of our data to fall within there. And so the first question you should ask yourself is, where the heck does this come from? And the fact that it's in books and the fact that I just told you so should not ever be satisfying. We want to know why this is the case. And so let's go ahead and let's play with R, because that's what Jim loves to do. He loves to play with R. And let's see where those values came from. So I'm going to use the function called qnorm. And what qnorm will do, and I also want to point out, notice that whenever we pull up any of these normal functions, it always says mean equals 0 and standard deviation equals 1. And that's because the default for the normal distribution is a standard normal distribution. And that's why everything is always mean of 0, standard deviation of 1. And so the qnorm will give us the value of a standard normal where we expect a certain quantile to occur. And so if I were to make this a little bit bigger, let's take a look at what this looks like. I'm going to use that cool function called curve, and I am going to use the probability density function for a normal. And again, I just give it x, and curve will figure out the rest for me. And I'm not going to even fill in the rest, but I could say mean is 0, standard deviation is 1. But since that's the default, I'm just going to leave it blank. And then I have to change the x limits. And I have to change the x limits because by default, curve will only plot from 0 to 1. And since we're dealing with a normal centered around 0, I would like for it to go, say, to -3 to 3. So we can go ahead and look at it. And there is our wonderful, wonderful probability density function of a normal with a mean of 0 and a standard deviation of 1. And so what we want to know, if we believe that 50% of our data should fall between the mean plus or minus 0.674 standard deviations, well, if it's 50% in the middle, that means that 25% must be below that part and 25% must be above that part. So what I will ask the qnorm function is I'm going to ask it very kindly, what is the quantile for 0.25? So you can think about that as I'm asking for the value down here on the x-axis. I'm asking at what value do I hit the 25th percentile? And so I go ahead and I do that. Hey, 0.674. That's what Jim wrote up on the whiteboard. See, I wasn't just making it up. And then we could do the same thing, qnorm, and I want to know the 75th percentile. And that's going to be positive 0.67. And so that's where this magical formula is coming from, is we're simply asking, 50% of the data equal tailed, then we expect 25% of it to fall beneath those bounds, and we expect 25% of it to fall above those. That should give us 50% of the data. We can further prove this to ourselves by using the pnorm function. And recall, the pnorm function is the cumulative distribution function. And so what we could do is we could say the pnorm, the cumulative distribution function of a normal, and then I want to take this quantile right here, that's the value, and then mean is 0. If we want, we could say mean is 0, standard deviation equals 1, if we want to do that to make us feel better. And so if I were to run that, I get 0.75. So 75% of the probability mass is below 0.674, all the way down to negative infinity. So what I want to remove from that is the probability that it's less than negative 0.67898, 644,898. And so when I do that, I get 50%. And so what's happening here is I can use this neat little function to add stuff to this, is I'm going to take this value here, and I'm going to use a function called AB line or AB line, and it'll draw a line on our plot. We'll see in a couple of weeks why it's called AB line, but let's just call it AB line from now, and it's going to be a vertical line that's going to be at qnorm equals 0.25. And then I could do the exact same thing and add a line that's at 0.75. And so 50% of our probability mass falls between negative 674 and positive 674. Over here, there's 25% of the probability mass, which goes all the way to negative infinity. And over here is the other side of the probability mass, which is also 25%, which will go all the way up to infinity, starting at 0.67. And so based on that, if we understand where those magical numbers come from, we could similarly say that we expect 95% of our data. Okay, we can do the same thing with thinking about where do we expect 95% of our data to fall. And we can get that number from the same place where we got the number for where we expect 50% of the data to fall, except here now it's going to be plus or minus 1.96. And again, we're dealing with a standard normal, so we don't have to multiply it by the standard deviation. If we had something where it wasn't z-transformed, then we would multiply it by the standard deviation, and it would give us what our expected interval is. And that 1.96 comes from where? Well, we can draw out that 976 again. Since we're interested in 95% of the data, that means that 2.5% of the data is going to be less than that, and 2.5% of the data is going to be greater than that. So I'm going to say I want the Q norm at 0.975, and there's my 1.96. That's where that came from. And then likewise, I could say 0.025, and that's on the other side. And so again, we could go ahead and we could draw our lines. 975 and 025. There. And so this is the 95% interval where we expect the majority of our data to fall. This is different from the 95% confidence interval. Do not confuse this with the 95% confidence interval. This is 95% of our data. And we could figure this out for any kind of interval. So if we wanted to ask what the 99% confidence interval would be, we could figure out what those magic numbers are by saying 995 and 9905. And so we expect 99% of the data to fall between negative 2.5 and roughly and positive 2.5. And again, these are all written as units of standard deviation. And so what I want to do is I want to do a little proof of concept, and I'm going to simulate data. And what I'm going to do is I am going to simulate pulling from a random normal. I'm going to take 10,000 draws from a population with a mean of 10 and a standard deviation of 2. And again, I'm going to set the seed so that way everybody will get identical answers. Whenever you do any kind of simulation or permutation, you should always get in the habit of always setting the seed. So I'll go ahead and I'll set the seed. And now I'll do that sampling, 10,000 samples done very quickly. So now I have this really long vector. And again, these are just data that are drawn from a normal distribution. And so let's take the mean of that. The mean of that is what? 10.022, pretty close to our what we know is the correct answer, because when we simulate stuff, we are the omnipotent being that knows everything. And so I'm going to go ahead and I'm going to call this mean.dat, and then I will do the standard deviation of dat. And for that, I can use the built-in function sddat. And so now I have the standard deviation. So that agrees quite nicely with what we simulated, which is good. It means the computer is actually working. And so we've sampled 10,000 things, and we estimate a mean of around 10, and we estimate a standard deviation of around 2. And so let's plot that data out, and just so we can take a look at it to see how pretty it is, because we went through all that work of sampling it. We should at least enjoy ourselves. So I'm going to use a function called Hist. Hist is going to just do a true histogram. And then the argument that I'm going to add in here is breaks. And I'm going to say 40. And what that's going to do is that's going to create 40 different bins that will fill up with things. And so there's the histogram of our sample. And that looks really pretty, and that looks nice, and we should feel good about that. And so we could ask the empirical estimate. So we have all these data. So if we wanted to know which one is in the 25th percentile and which one is in the 75th percentile, we could do that by ordering all of our data and actually figuring out this is the 25th percent of the way going through all of that data, right? And this is how percentiles are done, like when you get test scores back. Oh, you were in the whatever percentile. So there's built-in function in R called quantile, which will give us those quantiles. And I'm going to ask R to give me a quantile for DAT. And then I'm going to give it what quantiles I want. And I want it to give me two quantiles. I want the 25th percentile and I want the 75th percentile. And so I'm going to give it both of those, 0.25 and 0.75. And there is what I'm calling the empirical middle, those are the bounds of the middle 50%, where 50% of the data occurs. It occurs between 8.66 and 11.37. And I'll call that empirical because it's based upon our actual data that we simulated. Next, we can come up with what the theoretical expectation is. And that's going to be what? That's going to be the mean of our data, which is this value right here. There's our mean. Did I not do that? There's our mean. So we're going to take the mean, and we're going to add to that, I'll take the Q norm, right, the quantile of a normal, and I want 0.25 to start with. But now I have to multiply that by the standard deviation of our data because it's not z-transformed. And then I'll do the exact same thing for the 75th percentile. So again, here's our empirical estimates, and now our theoretical estimates are right there. And so this is using the probability density function of a normal distribution, and this is just simply taking the quantiles of all of our data. And what you can see is that they're pretty darn close to one another, which should be somewhat satisfying that the stuff that in theory should work actually works when we compare it against empirical data. And again, it works because we were correct in this case of modeling our data as random variables drawn from some normal distribution. And we could do the same thing with the 95% interval. That should work. Yeah, no, no. That should work. There, that encompasses everything. Okay, and so this is where we expect 95% of our data to fall. And then we could again do the same thing here where it's going to be 0.25 and minus 0.25. And again, it's 2.5 as opposed to 0.05 because there's two tails to this distribution. And if we want to know the middle 95%, that means that 2.5% have to be on one side and 2.5% have to be on the other side. And so we can look at, here's our, again, our empirical estimates, where this is actually where 95% of our data fell. It was between 6.10 and 13.966. When we do it using theory to tell us what should be done, that needs to be a negative. And yes, it worked. Again, really, really, really close. This is our theoretical expectation where we sit back and we say, I'm going to treat these as random variables drawn from a normal distribution. I've estimated mu, I've estimated sigma. Based upon that, the population writ large, this is what I expect to see based upon my parameter estimates. And it agrees very nicely with what the theoretical expectation is. All right. And so the next question you might ask, because I keep saying we have to assume that our data are random variables drawn from a normal distribution. one thing to ask is why normal? And there's a number of reasons why normal. Things in the real observable universe tend to be normally distributed, or many things tend to be normally distributed, or they can be easily transformed to be normally distributed. And so that's nice because we got this great tool that somebody invented called the normal distribution, and we can use it. The other reason why we tend to like normal is because oftentimes when we're developing statistical models or we're describing things, we're really interested in some description of the location. We want to know, is the mean of this group different from the mean of this group? Or how does the mean of this change when I add something to it, or if I change something? So we tend to be focused in on those location parameters. And one of the reasons why we like the normal distribution is because there's this thing called the central limits theorem. And the central limits theorem states that if you repeatedly sample a population and estimate the mean, the distribution of all of those means that you have estimated tend to converge on a normal distribution, which is pretty handy. And so I'm going to put together here a little bit of a simulation. And again, you don't have to sweat the code. Let's just make sure we understand what the code is doing, because now I'm going to actually put a little bit of real code in here. So first of all, I'm going to do some kind of a simulation. I always set the seed. Next, I'm going to just create an object. I'm not going to give it any values, but I have to create an object in order to propagate it with values. So I'm going to just say sampled means equals NA. And so what am I going to do here? Let's start with inside of this loop. The first thing I'm going to do is I am going to randomly sample from a uniform distribution. We know that a uniform distribution is not normally distributed, right? So if I were to just run this and then do a histogram of y, you can see that that is certainly not normal. And every time we do it, it'll look slightly different. And of course, it depends on how you bin things. None of these look that much like what we think of as a uniform distribution, but they would if we took a really, really large sample. Now it looks like a uniform distribution, okay? The point is that we know that this is not a normal distribution. But what we're going to do is we're going to sample 100 from that uniform distribution, and then we're going to just simply calculate the mean of it, and we're going to save that value of the mean. And then we're going to do it again and again, and we're going to do it 1,000 times. So the first time we go through, I is going to equal 1. So the first sampled mean that we have will be the mean of our first sample, and then it will loop through, and then I will equal 2. And we'll take another 100 samples or 100 individuals from that population, calculate the mean, and at the end what we'll end up with is 1,000 estimates of the mean of that population. And so again, we know that this is the underlying sampling distribution, right? It's a uniform. The reason why we love a uniform is it's really easy to integrate a rectangle. But now let's do a histogram of our sampled means. And look at that. It's normal. And so the central limits theorem is another reason why we like the normal distribution. And especially if we're mainly interested in those location parameters, this is where, you know, maybe in certain situations we don't have to sweat as much if the underlying sampling distribution isn't normal, because ultimately we're usually going to be interested in modeling the location parameter, or where we expect most of the data to fall. And so that is one of the reasons why we like normal so much, is because of the central limits theorem. And then just really quickly thinking about, just to review the idea of the law of large numbers. And you recall from the binomial lecture, the law of large numbers just simply states that if you if you have a large number of experiments or a large number of samples, your estimate for a parameter will become closer to the true value for that parameter. And I've done that again here. And this is very similar to what we did when we were playing with the binomial. So I'm going to start out by setting my seed, because I always got to set the seed. And then I am going to take, what is that? I'm going to take 100,000 draws from a normal population with a mean of 6 and or a mean of 10 and a standard deviation of 6. So now I have all those data in my computer. My RAM is happy to hold them for me. And now I'm going to pretend that I only sampled the first 10. So I can take the mean of what? The mean of y. Which ones? 1 through 10. 11.2, that's kind of close to 10, but you know, whatever. We can do the exact same thing with the standard deviation. Okay, so there's my estimate. Based on if I had only sampled 10, there's an example of what would happen if I only sampled 10. My mean is 11.2 and my standard deviation is 5.9. And then likewise, we can say, well, let's pretend, because I like pretending, that we took 100. 100 seems like a pretty good sample. 9.8 is now my estimate of the mean, and my estimate of the standard deviation is 6.9. It's like, okay, that's the best that we could do with a sample of 100. But what would happen if we sampled them all? So all 100,000. Now we're getting really, really good estimates. Right? And again, because we simulated this right here, we get to be the omnipotent, know-it-all beings. We know what the true unknowable mu is and the true unknowable standard deviation, or sigma, is. We know it. And this is our estimate based upon 100,000 samples. And if we went to 1 million samples, it would even be better. And if we went to 1 billion samples, it would even be better. And if we got to an infinite number of samples, it would be identical to the true population mean. But I'm reminding you of the law of large numbers. So that way you don't get really angry when people tell you that you need more replicates, because that's why. You always will have crummier parameter estimates the less information that you have. So when in doubt, always increase that. All right, let's take a quick break. Jimmy needs some water. All right, let's talk about the standard error. So another common statistic that people will present when they're trying to summarize their sample is they'll provide the standard error. And the standard error is different from the standard deviation and the variance in that the standard error is specifically talking about our estimate of mu. In particular, the standard error is describing the expected standard deviation of our estimate of mu if you were to repeatedly go to that population and estimate the mean. So it's about the distribution of possible means, and then it's the standard deviation based upon the standard deviation of those possible means, as opposed to being actually about your sample. Now, a lot of times people often like to show, when they're showing the results and they're showing a figure, they like to show plots that have error bars. And part of that, there's two possible reasons why people do that. I kind of feel as though one reason is because standard error bars tend to be small. And it makes your data look really nice if you have small error bars around it. But the other reason why we might be interested in doing that is that if we're trying to convey something about the mean as we've estimated it, the standard error will explicitly give us some kind of a visualization. The standard error bar will give us some kind of a visualization about our uncertainty around our estimate of the mean. And we calculate the standard error. Let me get myself out of the way. as such. And so the standard error is usually shown as S subscript Y bar. And again, S means standard deviation, but here we're talking about the standard deviation around our mean, which is why the standard error is also called the standard error around the mean. So it's often SE or SEM, and that's because it's going to be the standard deviation around our mean. And we calculate that by taking our observed sample standard deviation and dividing it by the square root of our sample size. Or the other way to write the same thing is you could take the full square root of the variance, of our estimate of the variance, divided by n. And this will give us an estimate of what the expected standard deviation would be if we were to have a sample of means. So again, the standard error is going to be about our parameter estimate for mu. It's not directly about the actual sample that we took. Rather, it's about the uncertainty around a statistic based on our sample. So let's just see like what this really means and why it might be handy. And so I'm going to go ahead and I'm going to do a simulation because I like doing simulations, because I like being the omnipotent being in a universe that I create. And again, you don't have to stress the code. You are not going to be asked to write these kind of loops at any point in this class, but it is worth knowing how to do it. So again, I'm going to simulate something. So I'm going to set the seed so that way every time I do it, it's perfectly repeatable. I'm going to create a blank object called sampled means, which I'm going to populate with means. And what I'm going to do is I'm going to loop through this loop 1,000 times. And each of those 1,000 times, I'm going to take 100 random variables from a standard normal distribution, so mean of 0 and a standard deviation of 1. I'm going to take that sample and I'm going to calculate the mean of it, and I'm going to save that mean. And I'm going to go through and do that 1,000 times. So what I'll end up with is 1,000 estimates of the mean from this population. And then I'll finish that by taking one more sample, because this will be our test case sample, where I'm going to take 100 samples. So here's one sample from that population. Here are all the values. And from there, I can calculate, obviously I can calculate the mean. Okay, so there's the mean of that one sample. And I can calculate the standard error. And the standard error is going to be the standard deviation of y divided by the square root of 100, because that was my sample size. And that is the standard error, okay? And again, that is describing what we expect the standard deviation to be if we were to repeatedly sample that population and calculate the mean each time. That is the standard deviation of the means. And so we've done this where we've gone to that population and we already have 1,000 samples of the mean. And so let's go ahead and look at what the standard deviation of our sampled dot means are. And you can see it's really, really close. Okay. So that should be satisfying that the standard error is doing what it's sold as doing, which is giving us an estimate of the standard deviation around the mean if we were to repeatedly sample that population. So again, keep in your head that the standard error is about the uncertainty of your parameter mu, whereas the standard deviation has to do with the spread of your sample around your estimate, or in principle, these are all estimates of the true population mu, which we can never know, and the spread of individuals around that estimate is what the standard deviation is describing with the probability density function of a normal, whereas the standard error is all about our uncertainty with estimating mu. And so this brings us to calculating a 95% confidence interval. And what the 95% confidence interval means is it is the range at which you are 95% confident that the true population mean falls. So a common misconception is that the 95% confidence interval describes where you expect 95% of the data to fall. And we've already calculated that when we first started playing with the normal distribution. But this is going to be something slightly different this time, where now the 95% confidence interval is the range where we are 95% confident that the true mean falls, taking into account our uncertainty for estimating the mean. Okay, so if we were to do that, because we know that the standard error is the standard deviation around the mean, we could borrow from what we did 45 minutes ago and simply say that we expect the 95% confidence interval to be our estimate of the mean minus 1.96. And remember, the 1.96 is that magical number for a standard normal distribution, where at negative 1.96 and positive 1.96 is where we have 95% of the probability density of a standard normal. And so we should be able to do this in the same way that we did before, and this will give us the area where we are 95% confident that the true mean falls. And this formula will work totally fine as long as we have an infinite population size or an infinite sample size. Now, obviously, we aren't going to have an infinite population size, so we have to account for the fact that our estimate of mu is going to get sloppier and sloppier, or less precise, as we have fewer and fewer samples. Remember the law of large numbers. If we had an infinite population size, then we would have a perfect estimate of mu. But since we don't, we have to account for the uncertainty that the lower the sample size we have, the more uncertainty we're going to have for our estimate of mu. And so what we need is we need a distribution that describes the sampling distribution for means. So we already have used the normal distribution for thinking about the sampling distribution from individuals from a population. But now what we need is a distribution that's going to describe the sampling distribution for means from that distribution. And this brings us to the t-distribution. And there are very few more distributions that we have to learn and understand in the class. I think that there's 3, and this is one of the 3, and this is the t-distribution. The t-distribution, so the t-distribution is probably one that you're familiar with because it's the distribution that's used for t-test, for example. And the t-distribution is going to be the sampling distribution for means, what we expect the distribution of means to look like. And the origin of the t-distribution actually goes back to beer. It was developed by someone working at the Guinness Brewery, and they needed a distribution so that they could kind of test the mean quality of beer from batch to batch to maintain some aspect of quality control. Because prior to that, they just simply had, you know, you drink it and you're like, it's close enough, and then you bottle it and sell it. And a guy named William Gossett developed the t-distribution so that there could be a formal statistical way in which he could look at different aspects of the beer, and ask whether or not batch to batch things were consistent. And so he developed this, and actually I was recently in Dublin, Ireland, and they actually have a little plaque here commemorating the fact that indeed William Seeley Gossett worked at the Guinness factory, and then he's credited here with developing the student t-test. He published it under the name Student because at that time, and probably still now, Guinness had very strict rules about publishing trade secrets, which makes perfect sense. But he was able to publish it under the pseudonym Student, and then it just pretty much went into obscurity, at least in regards to brewers. You know, there probably weren't a lot of brewers that were reading kind of esoteric statistical journals. And so he was able to publish it without giving away the fact that it was actually a trade secret that Guinness had to maintain the quality of their beer. And so let's look at a t-distribution. And to do this, I will use my favorite little function, curve. And I'm going to go ahead and I am going to plot a t-distribution. Now the shape of a t-distribution, if we do question mark dt, we can see that there's two important arguments in here for these. The first is we're going to want to know, you know, at what value do we maybe want to know the probability density. But the important parameter is degree of freedom. And so the shape of a t-distribution is going to change based upon how many degrees of freedom we have. And again, we can think about degrees of freedom in this case as being the number of individuals in our sample minus 1. Because since we're going to be modeling this based upon the mean, we've already estimated the parameter, our estimate of mu, which means that we no longer have, if we had a sample of 10, we no longer have 10 random variables, we only have 9 random variables. And so the shape of the t-distribution is going to depend on the degrees of freedom. The t-distribution itself is going to be centered at 0. So in that regards, it's very similar to our standard normal distribution. So let's take a look at what the t-distribution looks like. And here I'm going to draw up a t-distribution with 1 degree of freedom, meaning that we estimated our mean based upon a sample of 2, which gives us 1 degree of freedom. And the t-distribution looks something like this with 1 degree of freedom. Now that looks very similar to something that might be normal, but if you look at it for a little bit, it looks like the shoulders of it, the tails might be a little fat. And we can compare that against a standard normal distribution. And that's what a standard normal distribution is. So again, a t-distribution is going to have fatter tails. And it's going to have fatter tails because we're going to end up having more probability density mass on those tails than we do with the standard normal. And that's going to account for the increasing uncertainty that we have around our estimate of mu as we have smaller and smaller sample sizes. And so let's go ahead and we can add another one. I can draw a t-distribution with 5 degrees of freedom. And those 5 degrees of freedom means that we've estimated the mean based upon a sample of 6. 6 minus 1 is 5, so we have 5 degrees of freedom. And you can see that even by adding just those few samples, we're starting to get smaller tails and more of that probability mass is towards the center. Basically, it looks like it's starting to resemble more and more a standard normal distribution. And I'll go ahead and I'll do it one more time, in orange this time, with 10 degrees of freedom, meaning that with 10 degrees of freedom, we've estimated the mean with a sample size of 11. And now it's creeping up and it's getting closer and closer to what the normal distribution looks like. The tails are still a little fatter. And if I were to take this all the way up to, say, a t-distribution with 100 degrees of freedom, now it almost perfectly overlaps with the standard normal distribution. And in principle, if you had an infinite population size or an infinite number of degrees of freedom, then the t-distribution converges on a standard normal distribution. And so let's go ahead and take a look again. Here is our t-distribution with 1 degree of freedom. And I'm going to overlay on top of that a standard normal distribution. So that is a standard normal distribution. So again, mean of 0, standard deviation of 1. And in blue there is the t-distribution with 1 degree of freedom. And again, you can see that it looks like the tails are a little bit fatter. And so focusing on the standard normal, we could ask, where do we expect 95% of our samples to fall from that standard normal? And we've already done this, right? Where we said, where do we expect 95% of the samples to fall? And I can go ahead and I can draw those curves, right? And so again, we're using the Q-norm function at 0.025 and at 0.975. So this is where we expect 95% of our samples to fall. And this is just to illustrate that those fat tails are fatter than we think that they are, just by looking at them. And we could ask, well, where do we expect 95% of the means to fall with a t-distribution with 1 degree of freedom? And I'll do that in blue. And so this is where the 95% probability, inner probability mass of the t-distribution with 1 degree of freedom falls. And so you can see it's much larger. Those fat tails are a lot fatter than maybe they look. In some ways, this is an illustration that humans might be really poor at integrating in their head. But the probability, 95% of the probability mass falls between these two blue lines for the t-distribution, which is much broader than the 95% probability mass for the standard normal distribution. And so if we look at just how the t-distribution changes as we increase degrees of freedom, in addition to doing it graphically, here I'm going to ask for the quantile for 0.975 between 1 and 50 degrees of freedom. You can see again it's starting out with this 12.7, which is those really wide values that we saw when we looked at the 95% interval for this t-distribution here. And then it quickly, once you get to 2 degrees of freedom, it's getting smaller, and then here it's at about 2. And if we were to look at, say, what does the t-distribution look like if it had that many? So what is this? That's 50 million degrees of freedom. That's a lot of degrees of freedom. We get 1.959964, which is really close to our Q norm at 0.975. And the computer's actually telling us that it's the same value. It won't be the same value until you have an infinite degrees of freedom. But it's so close that it's essentially converged then at that point on a standard normal distribution. Right. Okay. And so we can prove to ourselves that this is indeed what the standard error, the standard error is describing, and we can then calculate the 95% confidence interval around the mean. So again, if we had an infinite sample size, we could use the same formula that we used when we calculated where we expect 95% of the data to fall in future samples. Here, we're going to be thinking about the 95% confidence interval, and the 95% confidence interval, again, is where we expect 95% of, or we're 95% confident that the true mean falls, and we would do it this way. So instead of using our kind of generic 1.96, which we would for a standard normal, we are going to adjust what that quantile is using the t-distribution. And so we're going to use the t-distribution. Alpha here is our confidence level. So if we wanted it to be at 95% confidence, we would calculate that by saying 1 minus that divided by 2. We're going to divide it by 2. Why are we going to divide it by 2? Because if we want the 95% interval, that leaves 5% left over, but we want 2.5% of that to be on one side and 2.5% of that being on the other side. And then we are going to multiply that by our standard error, which again, our standard error is our estimate of the standard deviation around the mean. And so these two things are actually very similar to one another. The important difference here being that this assumes a standard normal distribution, but we know that the sampling distribution for means is not normally distributed, it's t-distributed, and so we're going to use the value given to us by the t-distribution. And again, if n here were nearly infinity, it would pretty much converge to what we expect to see if we were to just calculate 95% of our data from standard normal distribution. And so this is what we would use to calculate then the 95% confidence interval. And so let's go ahead and we can do that. So I am going to just simulate some real quick data here. I'm going to say set.seed is 2, because I like doing that. I'm going to take, from a random standard normal, I'm going to take 100 samples. Now from that, I can calculate the mean, obviously. The mean is what? The mean of y. Nope, the mean gets the mean. There. So there's our mean. We can calculate the standard error then around y as being what? It's the standard deviation of y divided by the square root of our sample size. And here our sample size was 100, so the square root of 100. And that is our standard error. So that is the standard deviation around our estimate of mu. And so if we wanted to calculate then, the 95% confidence interval, we could say the lower dot CI is going to be the mean of y plus we will take the quantile of a t-distribution at 0.025, and our degrees of freedom is 100 minus 1. And then we're going to multiply that by our estimate of the standard error. So that should give us our lower bounds, and then we can take the upper bounds. So all we do is we change this to 975. And I got to change that to upper. Nope. There and there. And so this is our lower end of our 95% confidence interval. This is the upper end of our 95% confidence interval. So again, we're 95% confident based upon this sample, based upon that sample, that estimate of the mean, that is our maximum likelihood estimate of mu given our sample, and we are 95% confident that the true population mean falls between -0.2 and 0.19. And so let's do another pretend example, and let's make the data not centered around 0 and be a standard normal. So I'm going to set the seed again. This time I'll set it for 3. Why not? And then I'm going to take, from a normal distribution, I'll take a sample of, let's say, 10. And the mean is 8, and the standard deviation is 5. And so now I have all of these samples. I'm going to set my seed. I have all of these samples. This is my sample. I don't know what I sampled, but that's what I sampled, and that's what my measurements are. And so I can calculate the mean of that. The mean of that is going to be the mean of y. No, I gotta assign that, Jim. All right, and so there's our mean. Okay. Our standard error is going to be what? It's going to be the standard deviation of y divided by the square root of our sample size, which I will just say 10. And so there's our standard error. So if we were communicating this in a paper or in a talk, we might say that the mean was 7.66 plus or minus 1.36, and that's the standard error. Okay, that's the standard way in which we would describe that. So if we wanted to know what's the 95% confidence interval, again, we want to know what is the range of values that we are 95% confident that the true mean exists. We can go ahead and we can do that. So let's take, we have the lower dot CI is going to be what? The lower CI is going to be the mean of y plus quantile of 0.025, 10 minus 1, degrees of freedom times our standard error of y. That looks right to me. And then we can do the same thing to calculate the upper. The only thing we're going to change here is we're going to make this 975. And again, we're making it 975 because we want 2.5% of the variation to be below, or the probability mass to be below some value. And then here, this is going to give us where the cutoff is to be above that value. And then we'll have the middle 95%. And so that should give us what we want. So again, our mean is that, and we are 95% confident that the true mean falls somewhere between 4.5 and 10.7. And so we can, again, we can look and say, well, what happens if we had a larger sample? Because we know that the law of large numbers says with a larger sample, we should have a better estimate of our parameters. So let's run the same thing, but this time let's pretend that we took a sample of 100. So again, I'll reset the seed. So now I'm taking 100 samples. I'm changing it to the square root of 100 when calculating the standard error. So there's our new standard error. And we can modify this. And let's take a look now at what we got. So you can see that we feel that much better in our estimate of mu when we have a larger sample size. When we only had 10 samples, we are 95% confident that the true mean fell somewhere between 9.5 and 10.7. With 100 samples, now we're 95% confident that it's somewhere between 7.2 and 8.9. And you could play around with this and increase it to a sample size of 1,000 or 10,000. And your 95% confidence interval will get smaller and smaller because of the law of large numbers. The more information that we have, the more confident we are in our parameter estimate. As an aside, I want to point out that I've been doing this upper and lower by tapping into the 0.025 quantile and the 0.975 quantile. The other way that we could do the exact same thing is to stick with 0.025, except now subtracting it. And so these, if I'm right, God, I hope I'm right because this is kind of on the fly, these should give me the exact same answer. 8.904499, and then if I do it this way, yes, I get the same answer. And the reason is if we look at these quantiles for a t, and the same goes with a normal. So this is the 0.025 quantile for a t distribution at 99 degrees of freedom, is negative 1.98. And if I were to look at the quantile at 0.975, it's the same value, it's just positive. So there's just two different ways that you can do the same thing. It's a symmetrical distribution so that you know that the value of, the 5th percentile is the same, is going to be negative, but it's going to be the same, have the same absolute value as the 95 quantile because it's a symmetrical distribution. And I just wanted to point that out. These are both saying the exact same thing. When I did it this way, I just kept on adding things. And obviously here I'm adding a negative number. And so it's subtracting. Whereas here I'm adding a positive number. And that's going to give me the same thing as just subtracting that value, which is the same as adding that value. So they're the same. I just wanted to point that out because sometimes it can be a little confusing. Okay. One other thing that I thought that I wanted to do is, yeah, let's do this. Just one other way of kind of visualizing it and thinking about the difference between the two. And so here I am looking at I'm going to look at a standard normal distribution. Let's fix this. Let's see here. I simulated, what did I simulate here? I simulated y with a normal with a mean of 8, and so yeah, that should be pretty close. The SD is not found. Well, that's a problem, isn't it? The SD, the dot SD will get the standard deviation of y. Okay, so now I should be able to draw this up, and there is our normal distribution that we sampled these data from based upon our sample, based upon our estimate. And I'll go ahead and I'm going to plot up at the top here. These are all of our data that we have. Okay? And all of these data we believe are drawn from this population. Actually, we know that they are because this is based upon our maximum likelihood estimate of these data. And so the mean is right there in the middle. Okay, that red line indicates the mean of all of these blue dots, and then obviously it's going to go right through the peak here of the probability density function for our normal distribution. And so if we wanted to know the 95% confidence interval around the mean, I will go ahead, I've already created those objects, and so this is the range where we are 95% confident that the true mean exists given our sample of these data. That's different from where we expect 95% of the data to fall if we were to do future samples from this population. Those would be way out here. Okay, so we expect 95% of our data to fall between here and here, whereas we expect 95% of our means to fall within this narrower range. Okay, so this is just a visualization of the difference between thinking about the 95% confidence interval and just where 95% of our data are expected to fall given the parameters that we've estimated. So play around with that and make sure that you feel comfortable with understanding exactly what the standard error is describing, because the standard error will certainly come up again. It's a really important component for using the t-distribution for hypothesis testing as well as modeling other things. And so camp into your head exactly what the standard error is doing. It's the standard deviation around our estimate of the mean, whereas just the standard deviation of our sample is telling us about where our samples are falling relative to the mean. So standard deviation is about our sample. The standard error is about our estimate of the mean based upon our sample. And yeah, I think that kind of covers the t-distribution. It's a good one, so we'll use it a lot. You'll love the t-distribution. Okay, the last thing I wanted to kind of revisit is probability density functions. And I know that we talked about the probability of any given value drawn from a normal distribution is infinitesimally small because there are an infinite number of possible values from negative infinity to positive infinity that the normal distribution is trying to help us understand. But what we can compare are the heights on that density curve to think about which one is more or less likely. And so to do this, I've set up an example. I'm going to cut and paste it from the code that is posted, or should be. If it's not, let me know. Let's see here. Okay. I have a random variable from somewhere, and its value was 7. So based upon that, is it more likely that I got that from a population with a mu of 6 and a standard deviation of 5? Or is it more probable that I got that from a mu of 8 and a standard deviation of 6? So what we can do is we can use the probability density for getting a 7 out of either that distribution, mean of 6, standard deviation of 5, or that distribution, mean of 8, standard deviation of 6. And all we would have to do that is say d-norm. Yeah, d-norm. Got a little excited there with the density. And what is our value? 7. And we got a mean equal to 6. And we got a standard deviation equal to 5. And then we can do the same thing with the d-norm, where we got a 7. This time mean is 8, and standard deviation equals 6. Okay. And so we get these two different values. Okay. This one certainly appears to be more likely. It's more probable than this one. Again, these are not probabilities. These are probability densities. But what they're showing us is where these fall out on that plot. Okay, there's our two distributions that I've just kind of, just putting in a little part of it there. This is the black curve here is showing part of the curve where you have a mean of 6 and a standard deviation of 5. And the red curve is a mean of 8 and a standard deviation of 6. And so where those values are, or why we can feel more confident that the black one here is the more likely distribution that this was sampled from, is based upon that probability distribution. And we could do the same thing if we wanted to. And I'm going to just say, let's say that this is our sample. Okay. And here's our sample. Okay. All those values. And now we can compare two models. So now we're already starting to compare models, and we haven't even really built a model yet because we're using somebody else's model. That model is the normal distribution. So we have our sample of y, and we're going to model it as random variables drawn from a normal distribution. And let's say that there are two different possibilities that we want to explore. We either got those data from a population with a mean of 7 and a standard deviation of 2.5, or we got those data from a population with a mean of 7.2 and a standard deviation of 1.4. And so we can use the dnorm function. We could say dnorm of y with a mean equal to 7 and a standard deviation equal to 2.5. And now we have a vector of probability densities. And we could compare that against 7.2 and a standard deviation of 1.4. And there we have a vector of probabilities. Probability densities, not true probabilities, but just because they're densities doesn't mean that we can't play the old-fashioned let's multiply probabilities together. And so I can go ahead and I could take the product of this, which is just going to multiply them all together, and I can take the product of that, which is just going to multiply them all together. And that's going to give me the probability density for this, all of these data. That's the probability density. And then here is the probability density for 7.2 and 1.4. So just looking at that, what are we going to say to ourselves? We're going to say that it's more likely that we got this sample right here. It is more probable or likely, however you want to think about it, that we got that from a population with a mean of 7 and a standard deviation of 2.5 instead of from a population with a mean of 7.2 and a standard deviation of 1.4. Now this also brings up why, instead of thinking about just the likelihood, people like to always talk about log likelihoods and why we might want to log transform those probabilities. And you can see that quickly these numbers are getting really, really small because we're multiplying, because everything has a really low probability, and we're multiplying all of these really low numbers together. Eventually what will happen in the computer if you keep doing that, it's going to blow up. It's going to give you 0. And we know that 0 is impossible because everything has a probability, darn it. And so this is why we like to go into log land. And when we go into log land, recall that we don't take the product of things in log land. To take the product of things in log land, we simply add them together. So the arithmetic is easier. That's one reason why we really like it. The other reason is that computers have a limit as to how small or how big of a number they can handle. And with rounding errors, you're going to get to 0 and you're going to get nothing. But what we can do is we can say log equals true. Log equals true for both of those. So now they're in log land, and then all we have to do is take the sum of that. And we'll take the sum of that. Same inference as before. right? Because actually the numbers are the same, they're just in log units as opposed to being in raw probability density units. So we would look at that. This has a higher, let's call it the log likelihood. There's a higher log likelihood that our data, this data right here, there is a higher log likelihood that it is drawn from a population with a mean of 7 and a standard deviation of 2.5 than it is drawn from a population with a mean of 7.2 and a standard deviation of 1.4. Now, of course, we know that the best answer must be the one based upon our maximum likelihood estimates of the parameter. And so, or of the data. And so now let's do it where instead of saying the mean equals 7, let's actually take the mean of y. We know that that is the maximum likelihood estimate. We know that because we already talked about that. Likewise, standard deviation, let's take the maximum likelihood estimate. 0.5, okay. And so now, what did I do wrong? Standard deviation, oh, there's the problem, bam. And so that is as good as we can possibly get given our sample. It's better, it has a higher likelihood, a higher log likelihood than either of these two other options. And there is no other normal distribution on the planet that will have a higher likelihood than the distribution that's based upon our actual sample, our parameter estimates from our actual sample. Now that doesn't necessarily mean that it's right. What that means is that when we estimate the parameters based upon our sample, that's all we're never going to be able to get any better than that. But we can use the likelihoods to compare between different alternatives. Let's say that you had to decide what is more likely. Where did this sample come from? Was it from this population or was it from this population? Well, based upon the looking at the probability densities, that's the more likely between, you know, these two options, or even better, between these two options, we know which one is the more likely option, and it's this one. But the best option, clearly, would have to be the one that's based upon our actual data, which would be random variables drawn from a population with a mean of 7.033 and a standard deviation equal to 2.269361. So I just wanted to review that because we're going to keep popping back and forth at various times and thinking about likelihood. And so I think it's just kind of good to get your brain kind of primed for this. And also, this is a utility of the probability density. You know, when we were dealing with discrete distributions, it was really kind of straightforward, where we could think about what is more probable, the probability of this and the probability of that. And the probability mass function was giving us actual probabilities. So maybe it was easier for us to get our heads around. But we can use probability densities the same way. We just have to remind ourselves that they're not actual probabilities. They are probability densities. They're how far away that probability is from a zero probability, but they in themselves are not actual probabilities. And so at that is the end of our introduction to the wonderful world of normal. Next we'll talk, you know, obviously we're going to keep talking about stats because that's the whole point here. But when thinking about a normal, go through these little vignettes and go through the handout and the R script and feel really comfortable that you know exactly what's going on with all the different ways in which we describe a normal. Like, know what a standard error is. Standard error is all about a parameter. It's not about your data. Know exactly what mu is doing, know what sigma is doing. These will all continually come back. We're not going to understand how to do an ANOVA, for example, unless we understand really how variance is calculated and why it's calculated the way it's calculated. And what else did we do today? We learned about the t-distribution. That's super cool. The t-distribution, yeah, it's the sampling distribution for means. It's not the sampling distribution for our data. It's really handy to know. Understanding how the degrees of freedom, which is simply how many random variables do you have, affects the shape and your uncertainty around, around your estimate of the mean. In some ways, the t-distribution already knows the law of large numbers, and it knows that if you don't have large numbers, it's going to kind of say you don't have as good of an estimate as you think you have, and it's putting that slop in there for us. And so on that, I guess I'll just finish it with none of any of this stuff matters unless your underlying sampling distribution is actually normally distributed, which can kind of be a bummer. But we'll talk about ways, hopefully, that we can maybe get at fixing that next time. Or if not next time, the time after next time. Sometime. Cheers.